Right, we're getting there on differentiation now. I know it's got all quite tricky and everything. And today we're going to move on from trigonometric functions to parametric ones, which means, of course, we've got more than one definition going on. But don't worry, because we can use a variant of the chain rule, which was the first of the three things we've been using recently, in order to do that. And I don't think that this is particularly nasty. It's just a case of it's one more level of things on top of all the other different things we've learnt recently. But as with all of it, it's just a case of taking your time, doing one problem at a time, and practicing lots. And the more that we practice all the different sorts of things going on, the better we get at recognizing them. And so, of course, just have a go at this, and make sure you upload something to show me, like, at least one question where that you've really got your teeth into. Okay. Parametric differentiation then. So the chain rule variant is just that we're using t instead of u that we had before. And if you've got dy by dx times dx over dt, that is equal to dy over dt. Now what we're going to do is then change that around so that if x and y are given as functions of a parameter t, we want to know dy dx. And in order to do that, we need to divide dy dt by dx over dt. So we can say it's going to be dy dt divided by dx dt. So here's our problem. Pause the video, take a minute to write it down, and you might want to have a crack at it, because all we're going to do is use that bit in green above that we've just written down to work out what's going on. So this, of course, just means that t is within the set of real numbers. Let's have a crack at it. So we need to know, so we've got x, so we can say dx dt is going to be 3t squared plus 1, and we can say dy dt is going to be 2t plus 0, so just 2t. Now we know those two, we want to know dy dx, and that's going to be dy dt divided by dx dt. So that is 2t divided by 3t squared plus 1. And the original problem was asking us to find the gradient at the point P where t equals 2. So gradient at P is going to equal what we get when we slap 2 in there instead of t. So we'll have 2 times 2, which is 4 on the top, 3 times 2 squared plus 1, which gives us 4/13. And that's that. Okay, just one more question, one more example for today, and then we'll be on. Here's our final question then, and this is going to make us scratch our heads a little bit more, but actually it's not that tricky. Most of it is about straight lines and how we deal with their gradients, and it's all the same, it just looks a little bit nastier. So pause the video and have a little go and see how far you get, and then work through it with me again afterwards. So you'll notice I've popped the chain rule variant up here with it in the form that we're going to need it for. So the first thing to do is we're going to be using, instead of t, we've actually got theta, haven't we? So that's the only slight difference that we've got here from the question as it's been laid out for us. So if I do dx by d theta, using our circle of truth, we get 3 cos theta. And then if we go and do the same thing for dy by d theta, we're going to get negative 5 sine theta. And then we want to know about the gradient of y over x. So dy by dx is going to be dy theta minus 5 sin theta divided by the other one, which is 3 cos theta. Now, at this point, we need to know about it at this point here. Now you could plug it into your calculator like that, or you could think, I know that sin over cos is the same as tan, so I think I'm going to go for minus 5/3 tan theta. And now it's time to make sure you're in radians mode, and negative 5/3 tan, and our theta is pi over it, so gradient at P is going to be minus 5/3 tan of pi over 6, which is one of our known values, but we don't have to remember them, do we, when they're in the calculator, which is going to be negative 5√3 over 9. So that's the gradient of the tangent at P, and we need the normal, so it's at 90 degrees to that. So the normal is going to be 9 over 5√3. Now we don't really like having these on the bottom, do we? So it's going to be a good idea to just, you could times top and bottom by √3, or you can, if you like, just put it straight into the calculator, like so. Press equals and it will do it for you straight away. So that's what we know our gradient is for our equation at point P. And in order to find that equation, we need to set it up in the same way that we would do normally. Y equals mx plus c. So we know that it's going to be y equals 3√3 over 5 plus x plus c. And then at this point, what are y and what are x? So when theta equals pi over 6, x is going to equal 3 sine pi over 6, and we can whack that into our calculator. 3 sine over 6, and that's 3/2, which is a nice simple one. It's not going to be quite so nice, I doubt, for the other one. We'll have 5 cos pi over 6, so 5 cos pi over 6 being 5√3/2. And now we need to substitute this value for x and this value for y back into here to find out what c is, and then we'll be done. So we've got 5√3/2 is equal to 3√3/5 multiplied by 3/2 plus c. So I know my c is going to be 5√3/2. Take whatever this is, 3 times that is 9√3/5. 2's are 10. So if we do that, we can plug that into our calculator. 5√3/2 take 9√3/10, and that gives us 8√3/5. So we could say that our final equation is y equals 3 root 3 over 5x plus 8 root 3 over 5. But normally when it's looking like that and we're dividing everything by 5, it's probably nicer to put it in the form 5y equals 3 root 3x plus 8 root 3. But it doesn't really matter. They've asked you for the equation. That would get you full marks. Okay, so that is that. What I'd like you to have a little go at now is exercise 9G, questions 1, 6, 9 and 11. Now there are shed loads of them on question 1, so you might just want to do sort of 1 in every 3 of them or whatever, or enough until you, or all the basically different ones in there. There's about 10 of them or even more, I think it might be. So but do make sure you upload what you've done so I can see how we're all getting on. Okay, fantastic folks, see you next time.